Thank you for joining us on Synthesis Workshop. Today is a Research Spotlight episode, which has been made possible through a partnership with Team of Chemistry aimed at highlighting some of the great work done by Team of Chemistry Journal awardees. Today we have with us Stephen Koehler to present some of his work from the group of Professor Elizabeth Ilacqua, who received the Team of Chemistry Journal Award in 2020. Stephen was born and raised in Springfield, Ohio, and earned a bachelor's in chemistry from Duquesne University, where he performed undergraduate research on the reactivity of organometallic compounds in the gas phase under the guidance of Professor Michael von Stipdonk. After graduating in 2017, Stephen began his doctoral studies at Penn State, where he investigates the synthesis of sequence-defined donor-acceptor polyphenylene vinylines under the guidance of Professor Elizabeth Ilacqua. And from there, I'll let you get started, Stephen. Thank you very much for joining us today.
Thank you very much, Matthew, for that kind introduction. Today I'll be talking about some of our group's work in synthesizing donor-acceptor conjugated polymers through ring-opening metathesis polymerization, or ROMP. While we have diverse research interests in the Ilacqua group, all our work on this front is generally motivated within the realm of developing organic electronic materials, and more specifically organic photovoltaics. Back in 1995, Alan Heeger and co-workers developed the first bulk heterojunction solar cell from a conjugated polymer using methoxyethylhexyloxy paraphenylene vinylene, or MEHPPV, shown here, which is a highly studied and widely used material in many facets of organic electronics. These materials were developed and are continually studied owing to being solution processable, highly tunable, and possessing exciting mechanical properties in comparison to their inorganic counterparts. This work catalyzed a massive development of new conjugated polymers, altering the aromatic rings employed, modifying substituents to change optical properties or solid-state packing, which exemplifies just how tunable and customizable the materials can be. With this, the alternating donor-acceptor copolymer has generally demonstrated to be one of the most promising motifs for high-performance organic electronics. These materials can be synthesized in a variety of ways, the most rudimentary of these being iterative multi-step synthesis. The example shown here shows the reduction by Dibol followed by the addition of a benzyl phosphoester in the presence of base to induce a Horner-Wadsworth-Emmons type reaction. This can be repeated with another desired aromatic unit to synthesize a precisely defined sequence of conjugated oligomers. Of course, with each step, there is workup and purification, which makes this a rather time-consuming and inefficient method for synthesizing anything much larger. This does, however, demonstrate the impact of making small changes to the arrangement of these building blocks and the resulting optical properties as well as power conversion efficiency when tested as an organic solar cell. As it is shown here, the tetramer, which exhibits an alternating donor-acceptor sequence, has nearly double the power conversion efficiency of the next highest sample. Catalytic methods exist to synthesize polymers such as Kumada catalyst transfer polymerization shown below. In this example, the deactivated benzotriazole is known to undergo halogen-magnesium exchange more rapidly, which helps give control over the sequence of the resulting polymer. One downside of this method is that it uses a harsh Grignard reagent, which can prohibit the use of common functional groups from the scope, such as side chains containing carbonyl motifs and relatively acidic functional groups. More recently, there has been a growing interest in Suzuki-Miura catalyst transfer polymerization as a means of combating this functional group intolerance. However, this does not change the fact that neither of these methods work effectively for the synthesis of polyphenylene vinylines, such as the motif shown from the first example. In fact, there is a gap in the polymer chemist's toolbox of living polymerization techniques to synthesize donor-acceptor polyphenylene vinylines. Given the initial interest and prominence in PPVs, and now the more recently developed donor-acceptor polymers, we believe these materials offer an exciting opportunity at developing high-performance organic electronic materials, such as in photovoltaics. To begin, we took inspiration from work done by Michael Turner in 2006, where his group synthesized and took this highly strained conjugated molecule known as a paracyclophane diene, and allowed it to react in the presence of Grubb's second-generation catalyst undergoing ROMP, resulting in a living polymerization of PPVs. Using ROMP as the platform, we asked, can we synthesize a PCPD, or paracyclophane diene, comprised of an electron-rich and an electron-deficient aromatic ring to synthesize donor-acceptor PPVs with controlled molecular weights and molecular weight distributions? To achieve this, we followed some known protocols, making modifications where necessary owing to the differing reactivity of our acceptor unit. We begin by allowing a bis-alkoxybenzene to react with paraformaldehyde in the presence of HBr to install two bromomethylene substituents. Next, we add thiourea, followed by potassium hydroxide to convert the bromines to thiols. Similarly, we methylbrominated the benzothiodiazole using trioxane in place of paraformaldehyde to successfully achieve the transformation. Now we combine and dissolve molecules 3 and 5 in benzene in an addition funnel as shown on the right. We slowly added this to a dilute solution of potassium hydroxide and ethanol. It is important to add this slowly, usually over at least 2 days, to maximize the dilution of the reactants to favor an intramolecular cyclization reaction. From this point, given the asymmetrical substitution of the bisalcoxybenzene, there are 2 distinct inseparable isomers of the product. After some trials and investigating, we found these react indiscernibly from one another, so there is no need to separate them until the final monomer is completed. Next, we carefully generate benzene in situ by slowly adding tetrabutyl ammonium fluoride to a solution of molecule 6 and a trimethylsilyl triflate to induce a Stevens rearrangement. This step forms the desired carbon-carbon bond, and by oxidizing the resulting phenyl sulfide with peroxide to make it a better leaving group, we then heat it to 150 degrees Celsius in xylenes overnight to achieve the desired elimination of the 2 isomers as the final monomer. An important note for this final step is that even small amounts of acetic acid remaining from the previous oxidation step seems to kill the elimination, so performing copious washes with sodium bicarbonate helps tremendously. With the successful synthesis of our 2 monomer isomers, we look to realize our goal of synthesizing the first donor-acceptor PPV via a living polymerization method. This living nature should allow us to target molecular weights by adjusting the monomer to initiator ratio, all while maintaining a narrow molecular weight distribution. Additionally, ROMP is known to be rather functional group tolerant, and its mechanism is both sterically and electronically guided, so we hope to use both the electronic bias of our monomer to our advantage in controlling the resulting sequence. I will acknowledge that while we were the first to publish this, Michael Turner's group reached similar and exciting findings on derivatives of the same monomer a few months later. We began by screening various Grubbs initiators to ensure our polymerization would be complete and successful. We found that for the isomers shown, the entries A and E for Hoiveda Grubbs 2 and Grubbs 2 respectively yielded complete conversion after 36 hours. So these 2 seemed to be viable initiators moving forward. While not all initiators reached the complete conversion, all of them did exhibit low molecular weight distributions. We performed similar screening for the other isomers shown on the right. In this case, none of the initiators reached sufficient conversion, but again, all achieved low molecular weight distributions. Considering the lesser conversion, future polymerizations focused on the monomer on the left. That said, the difference in reactivity by varying the position of the larger alkyl chains is of considerable interest to our group moving forward. As this is largely a synthetic organic audience, I will take a moment to briefly explain dispersity or molecular weight distribution. This is measured using a technique known as size exclusion chromatography, or it is also sometimes called gel permeation chromatography. When a monomer is polymerized, very reactive chain ends form, which can result in polymer chains of different size, which I've color-coded here for easier viewing. This technique separates polymers of different sizes, where shorter polymer chains generally have fewer interactions with the stationary phase, causing it to elute more quickly, and larger polymer chains elute after more time. The polymers are usually detected with either UV vis-absorbance or a refractive index detector. When polymers are close enough in length or molecular weight, they may appear as a single peak. The larger this distribution is, the wider the peak will appear. Controlled polymerizations exhibit more narrow molecular weight distributions, such as shown here by comparison. Performing full polymerizations with varied monomer to initiator ratios, using Hoiveda Grubbs 2, shown here, we observed a strong correlation with the observed molecular weight, which was exciting for us to have this hypothesis partially confirmed. Additionally, at each data point, the molecular weight distributions were all below 1.5, so they remained low as with the previous trials, which is generally a threshold for a polymerization being deemed controlled. Trials using Grubbs 2 demonstrated effectively the same trend, which helps further confirm that we're able to achieve the first synthesis of a donor-acceptor PPV by living polymerization techniques. While this was all exciting, promising, and answered the question of if we can even make these materials, we still need to address and answer the question of how to control the sequence of this alternating copolymer. From here we have 2 questions, the first being, can we detect which of the 2 possible active chain ends form from the reaction? And from some preliminary data, which is not yet published, so I will not share it here, we are able to discriminate between these 2 chain ends using proton NMR spectroscopy. Similar data has been reported in 2 of Michael Turner's publications on the matter, which we have referenced below. Since we know how to track these, we can address our second question now, and that is, how can we control which of these forms? and that is just part of ongoing research endeavors within our group. Given that ROMP is both electronically and sterically biased, we're now looking at how changes in the alkyl substituents on our monomer can further dictate the resulting sequence. As I briefly alluded to earlier, given the two isomers of our monomer reacted differently with the same initiators, we believe strongly that this will be part of the key in achieving sequence-defined donor-acceptor PPVs. We have some bigger picture research endeavors surrounding this topic as well. As an organic chemist, I don't mind a little synthesis, but it cannot be ignored that the 7 to 8 step route can be daunting and time-consuming, especially for industrial applications. We're interested in finding ways to make derivatives more efficiently using some orthogonal syntheses, and of course have some ideas for abbreviating the route outright with some creative chemistry. And with that, I would like to thank the Alakwa group at large. Most importantly, Beth, who has been an outstanding mentor and advisor in my time at Penn State so far. I must also thank all the bolded graduate students and army of undergrads, even the ones who aren't bolded, but these were the ones who directly contributed to the project in varying degrees, and all have been invaluable. An extra special thanks goes especially to Maria Gregor, who is now under a different married last name, but for consistency in citations I kept the same. She did much of the preliminary work as an undergrad and is now doing wonderful things at PPG. And of course, I'd like to thank all you listeners for your time.
Thank you for tuning in for this Research Spotlight episode, and thank you to Stephen for a great talk. Thank you as well to Team of Chemistry for making this episode possible. If you enjoyed the episode, you can support us by subscribing and telling your peers about this podcast, and feel free to send us any questions or comments you have. Follow us on Twitter to stay up to date, and see you all next time.